Okay, so let's continue. So this is lecture 9, and before we start with today's class, let's actually refresh what we saw in the last class, because maybe I dumped a lot of information. So as the memories are all volatile, let's refresh them quickly so that it all stays put. So basically we were looking at 4 aspects of the LPTV systems. First, we tried to see what is the response of the system to any arbitrary input, and that was given by the convolution integral. So y of t is integral 0 to infinity x of t minus tau h of t comma tau d tau. And for the LPTV systems, we saw that this impulse response h of t comma tau is periodic in t, okay, and the time period is ts. And being a periodic signal, we decomposed it using Fourier series decomposition, and that told that any LPTV system basically can be modeled like this, where the input x of t goes through a bank of LTI filters, and the impulse response of these filters are basically the Fourier series coefficients of this impulse response, which we denoted as hk of tau, and these are the impulse response of each individual filter banks, and the output of these LTI filters are multiplied by complex exponentials. So at the other end also we have the same. Xt, and then we sum everything, okay. And this was first introduced or shown by Zade, and so we call this Zade expansion. And one point to notice, we know that we deal with real systems, so the impulse response h of t comma tau is real, right? But what about these impulse responses? Can you make comment on them? It need not be real, right? Because they are the Fourier series coefficients of the real impulse response, so they need not be real and they could be complex, right? And that is why when we looked at the conjugate symmetry, this was not true. That is, h conjugate of minus j 2 pi f was not equal to hk of j 2 pi f, right? Had this been a real impulse response, this would have been equal, right? Okay, so that's one point I wanted to make. And the second aspect we looked at was the response to a complex exponential, and that I denoted as e of t, and that was simply the h of j 2 pi f comma t, a scaling factor, times the input complex exponential e bar j 2 pi f t. And again, this is a periodic signal, so we could again decompose as using Fourier series, and that resulted in this term 2 pi f plus kfst. So the point is, to an LPTV system, if you feed in a sinusoid at a frequency f, at the output you could see frequencies which are f plus kfs, right? And this transfer function, which governs the translation from f to f plus kfs, these are called the harmonic transfer functions. Okay, so let us say at the input I apply a tone at f plus L fs. Okay, I know that at the output I can have a tone at f plus mfs. So what will be the harmonic transfer function governing this frequency translation? I'll have h, I'll have some frequency here. Yeah, it should be m minus l f plus lfs. Okay. So again, this is basically the input frequency, and what you write here is the difference between these. That's all. Okay. Great. And next, we looked at the conjugate symmetry that we have in the harmonic transfer functions, and that was basically h conjugate minus k of minus j2 pi f, and that was equal to hk of j2 pi f. Fine. And lastly, we also saw how one could compute this harmonic transfer function. And how do you do that? If you want to compute the harmonic transfer function, what experiment will you do? You have to apply a complex exponential, basically I'll just say e power j2 pi ft, which means you have to apply both cos and sine. Okay. And from there you can take two parts. Let's say if you apply this complex exponential, if you could directly write the output as sum of these complex exponentials, then whatever scaling factor you have, that will directly give you the harmonic transfer function. And in many cases you might not be able to do so. Oops, what happened? Sorry, just hold on. Right. And yeah, if you cannot do that, that is directly find what the frequency components are. What you can find is you find the transfer function, which is h of j2 pi f comma t, and this was basically the response to the complex exponential, which we write it as the response to the cos plus j times the response to the sine divided by the exponential, and you can find this and then take the Fourier series coefficients of this. Okay. And towards the end of the class, we also looked at the harmonic transfer functions of our dear old bandpass filter. So this was the bandpass filter we had. Right, this is phi 1 of t, and this is p of t. And for this, we computed few harmonic transfer functions. So when we apply DC f equal to 0, h0 of j2 pi 0 was, what was it? It was half, right? And similarly, we also found h1 of j2 pi 0. I think it was minus j by pi probably. And again, h minus 1 we computed, which was plus j by pi. And also we computed for frequency fs, and h0 of j2 pi fs was 2 by pi square, and h minus 1 was j by pi. Okay. And again, how did we compute it? We applied cos and sine, found the response of these two inputs, and then we computed h of j2 pi f comma t, and then took the Fourier series. Okay. Okay. And when we applied the cos and sine, we actually looked at the steady state response of the circuit. Right. That's what we did. Right. We saw the steady state, what was the capacitor voltages, and then we found the output voltage. Right. So why are we considering only the steady state response here? I mean, the question I'm asking is, we know that if I apply e power j2 pi ft to an LPTV system, I know the output will be h of j2 pi f comma t times e power j 2 pi ft. But of course, this is what we are breaking down as to experiment by applying cos 2 pi ft. I know here I'll get some yc of t, right? So where here is the idea of steady state response. Here looks like I'm giving a signal and directly looking at the output, right?
You are giving a sinusoidal.
Right.
Sinusoidal thing.
Okay.
There is no starting, there is no end of period.
Right.
It is like periodic from all the time.
Right. Correct.
That is why we have to check the final periodic signal. In
Yeah.
order to check the, if you want to check the periodic, basically you are trying to find the some harmonic, which means that some periodicity you are trying to check the output. That should be also seen without any initial transient, because initial transient
Yes. So basically, yeah, what he is trying to get is the actual signal that we have considered is this e power j 2 pi ft and cos 2 pi ft. But what does this mean? This signal exists from minus infinity to plus infinity, right? So the signal we will apply will be this, right? So it will be 0, and at t equal to 0, we will say the cos does this. Okay. So the circuit basically will take some time to attain a final response, and that's what will match the response to cos 2 pi ft, right? And that's why we are looking at the steady state response. Okay. If you could apply a signal of cos 2 pi ft directly, there is no need, but of course in practice we can't do it. That's all. Great. So now what we'll do in this class, we will actually see how we can simulate all these harmonic transfer function using simulators. Okay. And before getting into simulating LPTV circuits, first let me give a quick brush up of how you will do simulation for LTI circuits, because that's the procedure we had followed. We first look at LTI and sort of expand it to LPTV, right? And the thing that I'll be covering will be particular to Cadence Spectre, and because that's what most of you will be using and or already you would have been using, right? So, so let's start with simple LTI circuit. Let's consider this simple looking circuit where I have a current source and a few resistors. Say this is I in, and let's say the conductances of these are G1, G2, G3. So how will you solve this circuit actually if you are given this circuit? I mean, let's say I want to find the node voltages or the currents. KCL or KVL, right? One of them you'll do. So what is the first step in doing KCL? Sorry? Yeah, I mean find the nodes, right? Yeah. Basically here you have to identify the nodes in the circuit, and then you start applying the loss, whatever. And here you have to identify, yeah, meshes. Okay. So of course you can solve using either of the two or a combination of the two. But when, like, you guys are programmers, right? So let's say if you want to program a code, which of these two tasks do you think is easier? That is, given a circuit, yeah, because identifying nodes is pretty straightforward, right? It just says whenever you have two elements meeting at a point, it's a node. But mesh is not so trivial, right? You have to do some more, calculation. So simulators usually work with KCL, right? All simulators. And let's say you write KCL at these two nodes. Let me label 1, 2, and the voltage is V1, V2. Let's quickly write KCL. What is the KCL at node 1? So the current leaving the node 1 is minus I in, okay, plus V1 G1 plus V1 minus V2 G2 0. Similarly at node 2 I will have just V2 minus V1 times G2. Okay, and of course you can finally represent everything in terms of matrices. So let's say these are the unknown voltage vector. Okay, and let me put it here. So this will be equal to something, right? And first row in the matrix will be the KCL at node 1. Here we'll have the KCL at node 2, and again the same thing here, right? So this is basically the voltage V1 and voltage V2. So quickly tell me what the entries are for the matrices. So here it's G1 plus G2, here minus G2, minus G2, G3, fine. And here I have just I in 0, okay. So if you have any linear circuit like this, you can represent it like this: a G matrix times the node voltages is equal to the input current vector, and you can find the node voltages as basically G inverse times I in, right? Pretty straightforward. Something. Oh, 2 comma 2, right? Yeah, sorry, G2 plus G3. Yeah, sorry. Right? Yeah. Great. Okay. So, of course, the simulator will not actually first write the equations and then form the matrix. It will directly form the matrix, and it's actually pretty straightforward. If you look at the matrix, that the logic behind forming the matrix is pretty straightforward. So, if you look at the conductance G1, it is connected between node 1 and the reference node ground. So where is the entry for G1 in the matrix? It is in 1 comma 1, right? Only in the first row corresponding to V1 we have G1. Fine. Now similarly you take G3. G3 is between node 2 and ground. So we have it only in second row, second column. Fine. Now you take G2, that is between nodes 1 and 2. So we expect G2 to appear in both rows, right? So we have in the first row you have G2 minus G2. In the second row you have minus G2 and plus G2, right? So this seems to be a straightforward logic. And let us say you have some conductance in some circuit between nodes, say I don't know, I'll label it as L and P, and say the conductance value is Gx. So you'll form the G matrix, and let's say this is the Lth row, this is Pth row, this is L and P. So where what will be the entries for Gx? So on L comma L I'll have Gx, and L comma P minus Gx. Here it's minus Gx and Gx, right? And similarly, let us say there is some other node M. From there to ground you have, say, a conductance Gy. Where will the entry for this be? Only in M comma M, that's all, right? So let's say this is M, somewhere in between M, and here I'll have Gy, and all the others might be 0. Okay. So this is how the simulator will directly form the G matrix just by looking at the circuit. Okay, and then you can solve it. Great. So now let's make it a little bit complex. So now instead of this conductance G2, say I have a voltage source, the value V0. So how will you do KCL now? Huh? Sorry? Yeah, I mean you would have known, right? I mean you can either combine these two as a super node. That is one way. There is also another way, which is what he was saying. That is, see, the problem with having a voltage source is the following, right? So if you have this conductance, the current I1 that is flowing through the conductance is V1 times G1. That is, I know the relation between the node voltage and the branch current. But if I call the current through the voltage source as some current Ix, I cannot define what is the relation between Ix and the node voltages. So that's the difficulty, right? So what you can do is you can assume that Ix is an unknown current and write KCL, right? And if you do KCL, what do you get at node 1? Minus I in, that is the current leaving here, plus V1 G1 plus Ix equal to 0. Simple. Similarly at node 2, I'll have minus Ix, right, because current entering is Ix, leaving is minus Ix, plus V2 G3 is 0. Now how many unknowns I have? I have V1, V2 and Ix. So I need one more equation. So what is the third equation? Simple. V1 minus V2 is V0. Okay, and again let's quickly form the matrix. And in the unknown vectors, now I'll have 3 entries: V1, V2 and Ix. Fine. Here I have this. So again this is node 1, node 2. Here I'll have the equation corresponding to Ix. Again 1, 2. Ix or the voltage source. Okay. So again let's write it directly. The conductance G1 is between node 1 and ground. So I'll just have it here. The conductance G3 is between node 2 and ground. So I'll just have it 2, 2. Now let's look at the current Ix. So the current Ix is leaving the node 1. So if in the first row, which is where I am writing KCL for node 1, Ix will come with plus, right? So this will be plus 1. Okay. Similarly, the current Ix is entering node 2. So in the second row, I'll have minus 1. Fine. And the last equation is with this guy. So I'll have V1 minus V2 to be V0, and here I'll have I in and 0. Fine. And all the other entries will be 0. Is that clear? I mean, the point is, the moment you have a voltage source, you define the current through the voltage source as an unknown variable. You add it to the unknown vector list, right? Which means you need to have an additional row and an additional column, right? And you see that the current through this voltage source, it leaves a particular node and will enter another node. So for the row or for the node from which it is leaving, you add a plus 1, and it is entering the second node. So which means in the second row you add a minus 1. That's all. And you obviously have one more equation, which is V1 minus V2 is V0, that you add in the last row. Clear? So again, this kind of matrix formulation is called modified nodal analysis, or MNA. Okay, and simulators mostly will use this kind of formulation. Okay. And again, this again you can see you have a G matrix here, right? So this portion of the matrix has only the conductances, and then you have some other stuff here. Okay, so I'll probably write it like this. In general, for LTI circuits, okay, I can form the matrix like this. So I'll have a G matrix and then some A, B, C matrices. This times the unknown voltages and the currents through the voltage sources. This will be equal to the independent current sources and the value of the voltage sources, right? So here in the example we had only one voltage source. So we had another voltage source. You assume that the current through that voltage source is unknown. So you'll have again one more entry here. So one more row and one more column. Okay, great. So again, once you have this formulation, you can find this by simply inverting this matrix. Okay. So now let's again change the circuit. So instead of let's say this resistor, now I have a capacitor, right? And in this circuit, let us say I'm interested in finding H of J2 pi F. That is, let us say I want to observe how this voltage varies as the current, the frequency of the input current is spread from 0 to some value. Okay, so I want to have this plot. So now what happens, instead of having a G3, now we have a capacitance, and that will have an admittance. And what will be the admittance? It's basically J2 pi F times C, right? J omega C. So instead of having the G matrix, now instead of having a real number, you will just have a complex number. And of course, the complex number will change with frequency. So you form a G matrix for one particular frequency, invert the matrix, compute what the response is, and then you keep doing it for multiple frequencies, and then you can get the frequency response. Fine. And this analysis is in SPICE or in Spectre we call the AC analysis. Okay. Again, the simulator, what it will do, it will look at the circuit, right, and it will form the G matrix. This entire matrix it will form, and the moment you have frequency dependent elements, for each frequency it will compute what this matrix value is, and it will invert the matrix and find what the transfer function is. Straightforward. Great. So now let's go to more interesting circuits. So let's say you have a nonlinear but time invariant circuits. So I'll take a simple common source amplifier. I have a capacitor here. Say I have a small signal, and say I have a bias source connected somewhere. Okay. Now again, first let's say you are given the circuit, so and you are asked to find the frequency response. So how would you go about solving it? What would be the first thing that you will do? Okay. Let's say you have the models of the MOSFET. So how will you solve it? Huh? Yeah, but for doing small signal, what do you have to do first? You have to find the DC operating point, right? So first, what you will do, you'll find the DC operating point. And the MOSFET is basically nonlinear, so you'll have something like this. So let's say you're operating at this point. I know that around this operating point, if the signal is very small, I can approximate as a linear circuit. So once I find the operating point, I can find the equivalent LTI circuit, right? And once I find it, I'll do the same approach that I did. So for the LTI circuit, you can form the G matrix, invert it, and find the frequency response. Okay. So the point I want to convey is, for if you have just a LTI system, and if you are interested in finding the frequency response, you could directly run a dot AC analysis by skipping the DC analysis, right? You don't need to compute any operating point as such, because circuit is linear. So by looking at the circuit, I can form the G matrix. But this is a nonlinear circuit. So first I have to reduce it to an equivalent LTI, and for that purpose, for nonlinear and time invariant, you need to first run a DC operating point, okay, and then you can run a dot AC. Okay. And most simulators, when you simply run dot AC, they will run a DC operating point by default. Okay. But of course, you might not be able to access the result unless you explicitly say you run a DC operating point. But for LTI circuits, you can say that hey, you run AC analysis by skipping the DC operating point. You can set an option to skip DC operating point. The result will be same, right? Because for LTI, you don't have to do that. Okay. So now let's move to other circuits that are of interest to us. This is the LPTV circuits. And actually first let's consider nonlinear periodically time varying network that is varying at a rate fs. Okay, and let's say this has all the bias sources inside. Okay, and I am applying only a small signals. So just like how for the nonlinear time invariant circuit, the first step what you did was to find the DC operating point, and for that you de-energize all the small signal sources. So you'll have to do something similar here. You will first de-energize all the small signals, and you will try to find the operating point. But this is a periodically time varying network. So what can you say about the operating point? That will also vary periodically with time, right? So which means if I take any node voltage, say Vk of t, that will be varying periodically with time. So it will be periodic, say with a time period of Ts. Okay. So let's say the periodic operating point looks something like this, say between 0 and Ts, say just something. Now for the nonlinear and time invariant circuit, just add one operating point and you could simply find the equivalent linear circuit at that operating point. But here you see that the operating point itself is periodically varying with time. Okay, so at each of these operating points, you'll have to find the equivalent linear circuit for this nonlinear circuit. Just like how you found the small signal equivalent for the nonlinear and time invariant circuit. Now, at each of these operating points, right, we have to do the same. Okay, you can think of it as this. The best way to visualize it as, let's say at this point you have one LTI circuit, and in the next phase you simply change it to another time invariant circuit, right? That is one way to think about it. So for each of these circuits, you have to find the equivalent small signal model, and then you can find all the frequency response you want. So the first step here is to find the periodically time varying operating point, and once you have this information, at each of these operating points you can find what is the linear approximation for this nonlinear circuit, and then you linearize, and once you reduce it to a linear circuit, you can do all small signal analysis, right? Great. So now let us say we have an LPTV circuit at Fs. Again, there is no small signal applied. So here, what can you say about the node voltages in the circuit? They should also be periodic with time, right? I have not applied any excitation. The circuit I know is periodically time varying. So which means any node voltage, that should also be periodically time varying, right? And for example, if you take our band pass filter, so this was the circuit. Right? There is no input applied. Let's say phi1 of t and p of t. Now in this circuit, what voltages are varying periodically with time? I mean, I know definitely that this voltage is 0 and this voltage is 0, but that's not the entire circuit, right? I also have these fellows, isn't it? This is also, I mean, I have written it as a block diagram, but finally this will be going into some node, right? So basically in this circuit, these clock signals are the voltages that vary periodically with time. Okay, and of course because of these clock signals, the circuit is also periodically time varying, right? Because if the clock signals had constant values, the switch is either closed or open. Just add one circuit, no time variance. Because the control signal to the clock is varying with time, then the circuit is also varying periodically. So here the voltages that are varying are these clock signals. Okay. So I can say that even for LPTV, the node voltages will be periodic. So for LPTV, even though the circuit is linear, you need to find how this linear circuit is first varying periodically with time. Okay, that is, let's draw difference between LTI and LPTV. For the LTI circuits, the moment you have the circuit, I can form the G matrix and say G times E is IN, and of course your input can be time varying and the output will be varying, right? But for the LTV case or the LPTV case, you no longer have a fixed G matrix. The G matrix is also varying periodically with time, right? So you need to find what this G of t is. So this is how the formulation will be, right? that clear? I mean, at least even for this case, you can see for half the time the switch is open, so which means this resistance is infinity or a large value. So the G matrix will be of some form, and when the switch is closed, this resistance will be 0 or very small. So the G matrix will be of some other form. Right? The values in the G matrix will change. So the point I am trying to convey is, for LPTV circuits, this G matrix will be varying periodically with time. So unlike an LTI case where you could directly run a dot AC analysis, here I can't do that. First I have to find what is the operating point, right? Because that says how the circuit is varying periodically with time, and only from that I can find what G of t is. Okay. So here I need to run a DC operating point and find how it varies periodically with time, right? So I'll say find operating point of t. Okay, and once you have it, once you have this G of t, you can then do the small signal analysis. So that is one difference between LTI and LPTV. Okay, and of course, if you have a nonlinear time invariant, you need to run a DC op, and same for this also, right? Even if you had a nonlinear LPTV or a nonlinear periodically time varying network, you first have to run a DC operating point and find how this operating point varies periodically with time, and then you can linearize and then do the rest of it. Is that clear? So you can say run. Okay. And this task of finding the periodically time varying operating point is done using analysis called periodic steady state analysis, or PSS. Okay. So basically this is an equivalent of DC operating point, but for periodically time varying networks. That's all. Okay. So let's now see how PSS actually works to like at a very top level, and see how you can configure your simulator to set all the parameters properly. So PSS, as we saw, the main task of PSS analysis is to find how the node voltages in the circuit vary periodically with time, right? And as usual, for solving any circuit, you could resort to either time domain or frequency domain. Okay. And this time domain method of solving this periodic operating point is called shooting or shooting Newton, and this frequency domain analysis is called harmonic balance. Okay. Right. So in circuits where you have sudden jumps in your node voltages, such as our circuits where you had clock signals that was jumping abruptly, you usually use this time domain analysis, because let us say you try to solve in frequency domain to represent this abrupt jumps. How many harmonics will you need? You need infinite harmonics in practice, right? So obviously it makes sense that if you have abrupt jumps and like this, you use the shooting, and when you have slowly varying smooth transitions, then you could resort to harmonic balance. And today I'll just discuss about shooting. Probably later in the class I can discuss about harmonic balance. Great. And the way shooting finds the periodic operating point is this. So let's say this is my time axis. I know that in steady state, in the circuit, all the voltages vary periodically with time, right? So let's say this is time instant 0 and Ts. The voltage at these two time instants must be equal, right, in steady state. So what PSS will do, it starts with a guess for what the voltage could be at t equal to 0, and it will continue to solve and then find what is the value get at t equal to ts. Okay, and depending on the difference between these two and something known as sensitivity matrix, it will define this initial guess, and then maybe let's say it changes to it and then finds finally the right value. Okay. So yeah, that's all. At the top level, that's what PSS does. It has some initial guess and computes, and the moment the value at t equal to 0 and t equal to ts are equal, it means steady state is achieved. And of course, this has to be satisfied for all the node voltages in the circuit, right? Great. So this directly, I'll just write it. Compute steady state. And because of this, this PSS analysis, you could use it for some other applications also, or some other scenarios. And one such scenario is the following. Let us say you have an LTI, or actually a nonlinear time-invariant circuit, and let's say I have a small signal cos of say 2 pi f naught t. So let's say you look at any node voltage. What frequency components do you think it will have? It will have f0 to f0 and so on, right? It's nonlinear circuit. So what can you say about the time period of the node voltages? It will be 1 by f0, right? So I'll just say t0. Okay. So as I mentioned earlier, the signal that we could apply is this. Okay. Cos 2 pi f0 t times u of t. So which means to reach the steady state, the circuit could take some time. Okay. But let us say you are interested only in the steady state response. So now here you have a circuit where in steady state your node voltages are varying periodically with time. So you could actually use PSS to directly compute the steady state. Okay, because PSS doesn't care about anything, right? It just says you give me a circuit, and if in the circuit the node voltages are varying periodically with time, I'll directly tell you how it varies for one time period, right? So you can directly actually compute steady state response using PSS. Is clear? Because let us say you try to solve for all time instance using a normal transient analysis, your steady state response might be this. Let's say it attained a steady state, something, but from t equal to 0 it might do something, right? And then it might take long time and then settle to it. So if you have to run a normal transient analysis, you will have to run till this much time to see what the steady state is. But PSS doesn't compute all these transients, right? It just starts with an initial guess and quickly refines it so that it will finally compute, let's say, this portion of the waveform for one time period. Okay? Great.
So you're saying that PSS will be faster to...
Yeah, because it doesn't run all these for these time points. Great. And okay, let's see what are the parameters that you need. Let's say this is our periodically time varying operating point voltage. Say does something like this. This is t equal to 0 and ts. The values are equal. Ideally, you need to find this operating point for all values of time. But of course, in practice, you can't compute for all time instance. So what do? You compute only at discrete time instance, right? So what the simulator will do is it will take only finite number of time points, and these time points need not be uniformly spaced, because if the signal is very fast, it might take more and more points here to capture the change, and if the signal is very slow, it may take lesser number of points. Okay, and I'll call this, let's say there are 200 points here. So I'll define an average sampling frequency. I'll call it as strobe frequency, FST. So if, let us say, I have 200 time points within one period of TS, what can I say as the average sampling frequency for this? 200 Fs, right? So 200 Fs. Okay. So for PSS simulator, what are the information you need? One is this time period, TS. That is the frequency at which the system is varying periodically with time. And this is known as beat frequency in Spectre. And the second information is, of course, related to this strobe frequency. That is how many time points I have to sample in one time period. Okay. But instead of specifying this information directly, we have to specify it using some other parameters because of the following reason. Because let us say you manage to find decay of t for all time instance, a continuous signal, and it's a periodic signal. So I could find infinite harmonics for it, right? But now what I'm doing, I'm only taking finite samples. So I'll have, say, decay of n. Of course, they're not uniformly sampled, but these are discrete time points. So, and the average sampling frequency, I have told it as some FST. So it makes sense that the maximum frequency that you can represent will be related to, right, FST by 2. Okay, is it clear? And we know that for an LPTV circuit, if you give an input at F, at the output you will have F plus KFS, and even vice versa, right? Okay. And let us say you are interested in finding frequency translation from a large harmonic of Fs to, let's say, input F, or vice versa. You give an input F, you want to find how it translates to F plus a large harmonic times Fs. Now, since the maximum frequency you can represent in your system is now limited, that frequency from which you can consider the frequency translation will also now be limited. Right, because the maximum frequency you have is related to FST by 2. So you cannot actually exactly compute the frequency translations beyond this frequency. Is that fine? So I'll just say FST, it determines maximum frequency that we can consider for this frequency translation. And as an end user, this is what is of more interest to us, right? I don't care how many points you take in one time period. I want to find the frequency translation from, say, some frequency to some other frequency. So this seems to be a more relevant information for us, right? And that's what we usually specify through a parameter called max AC frequency. Okay. And this kind of sets the maximum frequency for frequency translation, and this will in turn determine the stop period. Fine. But as we saw earlier, we might not use PSS for computing the harmonic transfer functions alone. But as we saw in this case, we might be interested only in finding the steady state response. Right? So there, what you might be interested in is looking at the node voltages Vk of t and the spectrum Vk of, say, J2 pi f. Right? And of course, this is a periodic signal, and the spectrum will have, in principle, infinite harmonics. So if you want to look at, say, the spectrum till some harmonic, say some 50 or something, you need to tell the simulator, hey, please compute the spectrum till so many harmonics for me. Okay, and that's what is relevant if you are only interested in the steady state waveforms, and that can be specified using a parameter this number of harmonics. Okay. And that's because by default PSS computes only the time domain information, right? As we saw, it assumes an initial guess and computes the time domain information. So if you want to know the frequency spectrum, the tool needs to do additional calculations and show the spectrum. Okay. And the moment you set the maximum number of harmonics you need, even the stroke period should be set accordingly, right? Because if you want to represent some frequency, you need to sample it at a much higher rate, right? So this will also indirectly set stroke period, stroke frequency, and this will also indirectly affect the maximum frequency that you can have for frequency translation. Okay. And you might have this doubt: if I know Vk of t, I could directly compute the spectrum myself. So why do you need to specify this? But as it turns out, we don't know Vk of t for all time instants. We know it only at some discrete time instance, and most importantly, these time instants are not uniformly spaced. If we were to use an FFT algorithm to find the spectrum, we assume that the input to the FFT is samples which are uniformly spaced. But here you don't have it. So if you were to compute the spectrum using FFT, you will sort of approximate what the uniform samples might be and then compute spectrum which will not be accurate. Okay. But what the PSS will do is, based on these non-uniform samples, it has its own algorithms to exactly compute the spectrum. Okay. So that is why if you want to know the exact frequency spectrum, you need to specify the number of harmonics, and then the tool will compute so many harmonics with full accuracy. So to quickly summarize, we have two parameters. One is max AC frequency. This sets the maximum frequency for frequency translation. Okay. And if you are only interested in the steady state waveforms, you can specify the number of harmonics, and this is to specify maximum harmonic for spectrum calculation. That's it. And as we saw, the moment you specify a number of harmonics, that determines the stroke period, which will also indirectly determine the maximum frequency you can have for frequency translation. Okay. So this will also indirectly set this value, right? So obviously it makes sense that there should be some relation between these two parameters, and this is the relation. So the default value for max AC frequency is this. It is maximum of number of harmonics that you give, 10 times 4fs. Okay. For example, let us say you set the number of harmonics to 0, because say you are not interested in finding the spectrum of the steady state waveforms and only interested in the harmonic transfer functions. So if you set this to 0, by default, what is the value of max AC frequency? 40 fs. So you can find all the harmonic transfer functions and all the frequency translation till 40 fs by default. Okay. So yeah, and remember, just because you have set the number of harmonics to 0 doesn't mean that the time domain information of the operating point will not be correct, because even if you set the number of harmonics to 0, max AC frequency is set. Okay, and the moment max AC frequency is set, even the stroke period is set. So it will find sufficient number of points and it will give you the time domain information, but you can't see any frequency spectrum. That's all. And
Average stroke period.
right.
That is define an average stroke period, but that will not sample it at uniform intervals.
Yeah.
It will still sample it according to the.
Yeah, true. It just says the number of points to be taken in one period, that's all. Okay. And this average stroke frequency has this relation. It is max AC frequency times 5. Okay, that's the default value for the stroke period. I mean strobing frequency, and max AC frequency by default is set to this value. Right. So you can also write stroke period as, see, I will call this fellow as max harmonic. Okay. So then what does it become? Max harmonic times 20 Fs. So like I mentioned, what this says is, it will say that you take these many points in 1 TS when you find the periodic operating point. That's all. That's what the average stroke frequency means. Right. So now let us say you give number of harmonics to 0. Max harmonic you have requested is 10. So it will take 200 time points in one time period and find the periodic operating point. Okay. Great. So just to summarize, so PSS you can use for two things: finding the steady state voltages, periodic voltages and spectrum of that voltage, or to find the harmonic transfer function. And if you are interested in the harmonic transfer function, you are only interested to specify what is the maximum frequency to be considered for frequency translation, and that you can set using either max AC frequency or the number of harmonics, right? Because the number of harmonics also determines what max AC frequency is, but if you are only interested in the steady state, you only specify the number of harmonics. Is that fine? And so let us say you are we have an LPTV system and you are interested to find the frequency translation to or from 100 Fs. Now you can do two things, right? So one, I can set number of harmonics to 0 because I am not interested in the steady state spectrum. So I don't want to waste resources in computing the spectrum. I'll set it to 0. So which means the default value that max AC frequency takes, let me copy. Yeah, what is it? Is 40 Fs, right? But we see that we need translation till 100 Fs, so the default value will not work. So you need to manually set to 100 Fs. That's one way. And the second way, you can also directly specify the number of harmonics, right? And how much will you set it for? 25, right? You set it to 25 and it becomes 100 Fs. So if you set it like this, you can consider all the frequency translation till 100 Fs and also look at the steady state voltage spectrum till 25th harmonic accurate. Okay? Great. And let me also write the average stroke frequency is basically the maximum harmonic times how much? 20 Fs, right? Yeah, sorry. 20 Fs. This max AC frequency times 5, I mean basically, let's look here. Max AC frequency times 5, but I'm saying max AC frequency itself is this fellow. So, I mean, if you know in terms of 1, you can always find it. That's fine. So this is how you will probably set PSS, simulator, PSS analysis. So specify the frequency Fs, that is the time period or the frequency at which the circuit is periodically time varying, and then you either set one of these or both of them also, number of harmonics or max AC frequency. And once you have the information about the periodically time varying operating point, then you can find all the harmonic transfer functions, right? So let's say now we are interested in this fellow. I have computed all the periodic operating point information, so I know how the G matrix varies with time, and I can find harmonic transfer functions. And we usually are interested in two kinds of frequency translations. One, where I give an input at a frequency f and see how it translates at the output to f plus kfs. Second, I want to see at the output a frequency f. Okay, I want to see how much, that is how the frequencies at the input, which are of the form f plus kfs, they all fall back to f at the output. Okay, and usually, we can. There are two different simulations for these, and this can be run using a .PAC, which is periodic AC analysis. So here you specify the input frequency, and it will tell you how this frequency is translated at the output around each harmonic, right? And if you want to do this, that is, you want to find how a frequency at an output f, or how a frequency f at the output is, the contribution of it is coming from the input. That is, how frequencies at the input, which are of the form f plus kfs, they contribute to a frequency f at the output. Then you run an analysis called .PXF. It's called periodic transfer function. And the good thing about this is you can do it from multiple input sources also. Say for example, you have an LPTV and you are providing the input to two different nodes. Like we have two different input sources. From each of these input sources, in one shot you can find how the frequency f is coming. Okay? And basically you need two different simulations here, because in the first case I need to specify, or I have to apply an input at a frequency f, one experiment, and then I'll find at the output what are the frequency components present. But for the second case, I have to apply an input at f plus kfs. So which means I have to do multiple experiments and then find what is the output at a frequency f. So it makes sense that these two must be two different analyses, right? And we'll see later that how instead of doing multiple experiments, by doing one simple experiment on some other circuit, we can calculate this in one shot. We'll see it in later half of the course, and that's what the simulators will also do. Okay. So is this fine? Yeah, same thing. Exactly, yeah. Like I mentioned, before running any small signal AC analysis, for periodically time varying networks, you need to run the PSS. You need to compute the operating point. There is no escape. Okay. So here I have wired up a circuit, and what circuit is this? It's a band pass filter that we have been looking all along, right? And this is the switch R and C, and this is basically the multiplication P of V. Okay, and I have given R and C such that the RC bandwidth 1 by 2 pi RC is 10 kilohertz. Okay, that's how I have chosen this value. So So actually first let's look at PSS, how we'll use it to find the steady state response. So let's say I'm applying a sinusoid, it's an amplitude 1, phase 0, and say input frequency equal to Fs. I've chosen Fs to be 10 megahertz, right? And let's say it's 10 megahertz. And here I have given a sinusoid at a frequency equal to Fs, right? So what will be the output here? Last class we sort of looked, right? If you had a sinusoid and the switches are on for half the time and it is off for half the time, it will be 2 by pi, constant value here 2 by pi, basically the average of the positive half cycle. And when you multiply it with 1, 0, you'll have a square wave, right? So actually first let's do a normal transient analysis and try to find that steady state. And I already computed that you have to run it for 400 microseconds. So let's run it. And you see that it doesn't immediately settle to the steady state, it takes some time, right? And let's say after this point, you see that it's a square wave as we expected. Fine? Okay. And let's look at the time it took for computing. The time elapsed is around 3.8 seconds, right? So let's actually try to compute the same steady state response using PSS. Let me actually delete everything so that I can set it. So as usual, we need to set first the beat frequency, and it usually auto calculates from the circuit because I have two sources. One is the clock and one is the input sinusoid. So whatever is the common frequency, it will take it. And here is the number of harmonics you have to specify. So now I am not interested in finding the spectrum, so I'll just make it 0. And max AC frequency by default is 40 times Fs. So I'll have good number of points to be captured. Is that fine? So I'll set the accuracy to moderate and just run it. Okay, so let me quickly run it. Yeah, it's done. So now we'll just look at the waveform. PSS, I'll look at the time domain, and this is the voltage. And you see directly computed the steady state, and the value is also matching what we expect actually. Okay. And now if you look at the time it took for it, it's basically 0.38 seconds, right? Even for the small circuit, you see it's sort of 10x faster, right? So you can imagine if you have complicated circuits with long transients, you might as well use PSS to directly find the steady state. Okay. So now let's actually look at the harmonic transfer functions, and for that I'll not give any input, everything is DC. So here I'll set the magnitude of this is basically the for PXL, for finding the translation from F plus KFS to F, and if I say the magnitude is 1, it will apply a 1 volt sine and cos, right? That's all. Here again PAC use it for finding the translation from F to F plus KFS, and again I'll say that you use a 1 volt sinusoid for computing phase 0. So now I have set PSS, so now I need to set PAC. Okay, and last class we computed few values, right? So let's see if they match. And here you can specify the range of frequencies. So this is the value of F you want, right? And let's say I'm interested in only 1 point for now. I can give a single point. And in the last class we have sort of computed some values. Yeah, so these are the values, right? Oops. So I'll first give an input F equal to 0 and then see these values. So I'll specify the frequency as 0. Okay, and here it asks for the sideband, right? So what this means is till how many harmonic I have to compute it. For example, this computes the translation from f to f plus kfs. What is the maximum value of k I have to use here? I should compute. And of course, this cannot be greater than the maximum AC frequency I've set, right? Now the max AC frequency is 40 fs. So till 40 you can exactly compute. Beyond 40 it might not be correct. So let's say I'm interested in only 2 for now. I'll just give randomly 2 or 3, whatever. Doesn't matter. I'll run it. Look at the results in PAC. And yeah, I'll directly look at the voltage spectrum because I have given a 1 volt input. If I directly look at the output, that's the transfer function, right? So I look at the output. This is the spectrum. So here you see, I see a tone at DC. That is, the strength is, actually, I don't know if you can see, it's minus 6 dB. So let me see if I can mark it. Yeah, it's minus 6 dB. And that's what you expected, right? Half. And this is the tone at Fs from DC to Fs, and that's minus 9.94 dB. And what is the transfer function that governs this this translation? Huh? Sorry? H1. I mean, input is 0, output is at Fs. So it's H1 of J 2 pi 0. And we had calculated it to be 1 by pi, right? The magnitude is 1 by pi. So let's see if it's actually correct. So 3.4159. Yeah, that's minus 9.343, and that's what we get. Okay. And in the last class also we saw when you apply a DC, that is, you apply a DC here. This will also be a DC. At the output, you'll have a periodic square wave with 50% duty cycle. So what can you say about H2 of J 2 pi 0? 0, right? There are no even harmonics. And that's exactly why you have literally minus 140 dB is close to 0 for all practical purposes, right? It's 0, and again you have at 3 Fs. Okay. And you can also compute the PAC for a range of frequencies. And in the last class we also saw, right, the transfer function or the frequency response for the bandpass filter, where I apply a frequency f at the input and observe what is the response at the output at f, and that was basically H0 of J 2 pi f, right? So let me try to plot this also, and it's also straightforward. Instead of giving a single point for the frequency, you give a start to stop. So let's say I give started from 0 Hz to 50 megahertz, that's basically 5 Fs. I am sweeping the input frequency from 0 to 5 Fs and see how it's getting translated at the output at the same frequency. Okay, here I specify linear stick, and I'll step it to, I'll make sure it computes at every 1 kilohertz so that you have a smooth plot. So this could take a few seconds. Okay, again PAC, I'll directly look at the output spectrum. Okay, so now we have a lot of curves, and you can see here. So this portion where it says 0, that is basically the translation from the input f to the same frequency at the output. This is the f minus fs and so on, right? So let's say I'm interested only in H0, I'll disable other ones. So we'll have this, and as expected you have multiple bands. So first band is around DC, second band is around Fs, this is at 3 Fs and so on, right? And at DC we know the value is half, right, DC gain, and that's what you have, minus 6 dB, right? So let's quickly look at the bandwidth also. I had set the RC bandwidth to be 10 kilohertz, and here I am switching the switching the resistor only for half the time. So what will be the single-sided bandwidth? Huh? Yeah. So I said 1 by RC to be 10 kilohertz. It should be 5 kilohertz, right? If I look at single-sided bandwidth, it should be 5 kilohertz. If I look at double-sided, it should be 10 kilohertz, right? So let's look at double-sided. So this is, yeah, actually let's look at this gain also, right? Hold on. Yeah, at 10 megahertz, I see that the gain is minus 13.86. So what harmonic transfer function is this? Huh? I mean, this I'm applying an input at f, observing the output at also at f. H0 of fs, right? Input is at fs, output is also at fs. H0 of j2 by fs, and this is what we calculated earlier, and that's 2 by pi square. And let's also confirm it quickly. So this is 2 by. Yeah, that's around minus 13.86, right? And that's what we got. Okay. So now let's look at the bandwidth. So this is 13.86. So 3 dB lower is 16.8. Let's say approximately this. And you see, I don't know if you can see, bandwidth is 10 kilohertz, right? That's right. And if you want to find the translation from, say, input at f to output at f plus 1 fs, you look at this transfer function, and we didn't compute that, but of course if you compute you will have this also. Okay, you can't see it, huh? Okay. So let's also look at PXF. Disable this flow, and from our calculations we can see, if I apply, I mean, this h minus 1 of j2 by fs, what does it say? I apply a tone at fs, observe it at DC, right? So I can compute it using PXF. So I'll say I'll apply output frequency is at DC. I'll ask it to compute what all frequencies at the input is resulting in a DC component at the output, and that can directly give me this. Okay. For this PXF is there. I'll again look at only 1 point for now. So this is the frequency that you are interested at the output, right? I am interested in DC at the output, and here again is the maximum sideband. That is from how many sidebands from the input you want the frequency translation. I'll just say probably 3, and you have to tell what is the output you are interested in, right? So I'll set the output voltage. These are the nodes I am interested, and that's all. So now it will tell at this output node between Vout and ground, the output at DC, it will compute, what frequencies at the input are contributing to this tone at DC at this node, right? So let's run it. It's done. PXF. And yeah, so now I need to specify what is the input I'm considering, right? So from which input I'm considering the frequency translation. This is my input. Yeah, once I do it, I get this. So what this says is, this is the frequency at the input. Okay. So from DC at the input, I have a contribution to the output DC, and as expected, that's half 6 dB, right? And this is the tone at fs, 10 megahertz. That is, an input is at 10 megahertz, which is fs, and how it translates to DC at the output. And that's around 9.94, and that's equal to 1 by pi, right? And of course, you don't have to restrict here. You can give a range of frequencies instead of a single point and see. Okay. And let's say now, for example, give a 1 kilohertz. Yeah. So now I've given the frequency as 1 kilohertz. So it will tell what are the frequency components at the input that have resulted in this 1 kilohertz tone at the output, right? And probably let me see. I can have basically I want an output output is at a frequency f, so I can have f plus fs. Can you see this? F plus fs can contribute to an output at f, and similarly f minus fs will also give it, right? And this, what is the frequency or the harmonic transfer function for this? H, I'll say minus 1 of f plus fs, and for this h1 of f minus fs, right? So let's say I want to find this fellow. Okay, so the frequency here is what? F minus fs, which is basically a negative frequency, right? Simulators will work with positive frequencies, right? So this is where you can use conjugate symmetry, right? So I know that if this is what I'm interested in, okay, so this I can also find by doing h conjugate of minus 1 of the negative frequency, which is minus f plus fs. That fine? These two are equal, right? We saw from conjugate symmetry, and this is basically, we have already, instead of computing this, you can as well compute this, and the magnitudes of these two will be same, right? And even if you look at the plot you have here, you will actually see two tones. One is basically fs minus f, and other is basically fs plus f. Okay, and that's because you have this fellow, right? F plus fs we know, and instead of computing at f minus fs, it has computed at fs minus f. So this is basically this quantity is equal to this in magnitude, right? This is where you use conjugate symmetry. Okay, so yeah, we can run over time, so let's stop here.
Instead of f minus fs, we replace f minus f.
Fs, yeah.
So it's minus f minus fs.
No, sorry, you say again.
So if we take the
One second, let me just stop recording.
frequency or just x?
One second, let me just stop it.